Hello, good morning, good evening, good afternoon, everybody, wherever it might be. Today is my great pleasure to introduce SUGATO MUKHOPADHYAY. He used to be an impan, right? But then he betrayed us and came to SISSA. So, but anyway, silly jokes aside, we are very happy to have him in person here in Trieste, giving a talk on his joint work with Ludwig Dąbrowski and Jan Liu, who are present here in the audience. I mean, I can show them to you. And the title is Algebraic and Spectral Torsions on the almost commutative geometry of doubled manifolds. The Zoom is yours, the floor is yours, take it away.
Thank you so much, Piotr, for the introduction, and thank you for allowing me to give this talk. So, yeah, like as you mentioned, and it's written here that this is ongoing joint work with Ludwig and Jan, and hopefully soon we will wrap up. So the talk is broken up into 4 parts. So for the first part, I will be talking about first order differential calculi, focusing only on spectral triples, not on general abstraction. This will be because I will be mentioning the recent published work by Dąbrowski, Shikaj, and Zaletsky on spectral.
I'm impressed by your pronunciation. You said it perfect Polish. So you're saying the impan wasn't wasted. Okay.
So to even introduce the notion of spectral torsion according to DBZ, FODCs are a key ingredient. But my main intention is to compare the notion of spectral torsion with slightly more previous abstract notion of algebraic torsion. For that, the main ingredient will be second order differential calculi. So this is the order that we will go through. Right, so first order differential calculi. So for spectral triple AHD, where A is of course star algebra, maybe dense in a C-star algebra. H is the Hilbert space admitting a faithful representation of A, and D is a typically unbounded operator densely defined on A, satisfying some regularity properties. Let's not go through a list of 7, whatever. Then any FODC on it is given by the pair omega 1 D and well, comma D, where this small d is a map going from A to omega 1 D defined by the commutator of A with D, and this is called the exterior derivative, and the omega 1 D, which is left A-linear sum of these commutators. These are called the bimodule of one forms. So let me give an example. The most basic example other than the trivial one, which is that of the 2-point space. I guess this is partially named after you. Yeah. So there's a Conran spectral trip. So I denote the 2-point space by the symbol Z2, even though I will not be using the group structure for this talk at least. This is just for convenience.
I'm sorry, I'm confused. Yeah. Do you think is Z squared or Z2?
So Z2. This is a typo. This is a typo.
Yes.
Z2. I'm sorry.
And by the way, this typically stands for p-adic integers, not for proportions. So it's much better to have Z divided.
Yeah, okay, sure.
But anyway, this is what you mean, 2-point.
Yeah, 2-point. This is exactly that. I hope it doesn't occur again. So yeah, the algebra A is basically complex functions on 2 points. So they are basically generated by 2 elements, E plus and E minus. My Hilbert space will be the C2. This is 2 above. Yeah, and let's say mostly trivial Dirac operator over here, which I denote by D2, is this self-adjoint off-diagonal map parameterized by a complex number phi. So the algebra is embedded in BH diagonally. The bimodule of one forms, it's a very trivial computation. It is known that it is generated as a left module. I remember from the last time. Is generated as a left module by just one element, which is d of e plus. We could have also chosen d of e minus. It would just be a change of sign over here. So the second example, which is my main focus for this talk, is the almost commutative geometry of doubled manifolds. So what this says is that, by the way, let me just go back once more. So here the algebra, you see this is a commutative algebra. So, and it is finite, but still because of this non-trivial Dirac operator, we still managed to get a non-trivial differential calculus. Right, now the almost commutative geometry of double manifolds. So this is a spectral triple on n cross Z2, where let C infinity M, Hm and Dm be a spectral triple on the manifold, and you can take as nice spin manifold, even dimensional, all those regularities I'm not really bothering so much about. And then the algebra is C infinity M of M cross Z2, which is isomorphic, I should say, to C infinity M tensor C Z2. And the Hilbert space is H, which is a direct sum of H plus and H minus. Both of these H plus minus are isomorphic to Hm. And the Dirac operator over here is the diagonal coupling of each dm on the manifold, and then sum of a grading operator tensored with the Dirac operator we just saw on CZ2. So a grading operator which defines incidentally an even spectral triple, then it satisfies this following formulae that A gamma is equal to gamma A, D gamma equals minus gamma D, and self-adjoint gamma is unipotent. The algebra again is similarly embedded in B of H, that is one copy of C infinity M goes on the top left corner, and another copy of C infinity M goes on the bottom right corner. Generic element of omega 1 dA, this is a slightly more tedious calculation, but in the end it turns out that a generic element is of such a sum form where omega plus minus are one forms on M. These are embedded diagonally, and this off diagonal part, which where f plus minus are functions on C infinity M, and and I have just cleaned up the notation a little bit, where this phi gamma will be from now on denoted as chi. And let me just point out that in the 2-point case, you could pretend that M was a point, and then this D would vanish, and we would recover the example that we just previously saw, where the diagonal part will vanish, and we'll be left with these things, and F plus and F minus will be just complex numbers instead of functions, because then C infinity M is a point. Right, so spectral torsion, this is the part which I am the most shaky about. This is not my own work. This is, first of all, let me just briefly mention the notion of non-commutative residue due to Cohn-Moscovici and later some results by Hickson, which is that let AHD be an n-summable regular spectral triple. Then there exists a trivial state W on the generalized algebra containing A and D times mod D to the power L. I didn't want to throw in the word pseudo differential algebra differential operators, just yeah. And so this trace is called a non-commutative residue. Typo. Curly W vanishes on T mod D to the power minus K for any K greater than N. That is, if once the power of mod D becomes sufficiently low, W kills this operator, and where T is an operator generated by just the algebra A and omega 1D. Right, so this is the result by Domkovsky-Zaletsky, very recent paper, as you can see. So,
may I ask a stupid question? I'm puzzled by your phrase generalized algebra. Do you mean that the concept of algebra is more general?
No, it's
extended algebra.
It's extended algebra.
Okay.
Maybe if I had said mentioned pseudo differential operators,
Yeah.
it would have been.
Okay.
Mm-hmm. Yeah. So using this non-commutative residue, GS said defined functional, which is trilinear, that is, it admits three entries of one forms, and using the this non-commutative residue, they define this to be the spectral torsion functional. This should have been functional. So, and they say that the Dirac operator is called torsionless if T vanishes identically. So, example of, in this paper they had 4 examples, but only in the case of one, really one concrete example where they get torsionless torsionless Dirac operator, which is of the example of the double manifolds.
Torsion full.
I'm sorry, torsion full. This is the problem of leverage of people. Torsion solved by less. Torsion, yeah, with torsion. Yeah, with torsion. Right. So again, we recall that the algebra of almost commutative functions, which again I'll mention that it means that the algebra itself is commutative, but the differential calculi is non-commutative. It decomposes into a diagonal part and an off-diagonal part. So first of all, they find that the product Dirac operator for a closed spin manifold M, if this M over here were a closed spin manifold of dimension 2m, then the product Dirac operator, which I had just mentioned before, so then it is not identically 0. I think the barrage of formulas is going to come now. Yes. So they compose 4 cases where, as you might recall, that the residue takes in 3 one forms. So they consider the combinations diagonal, 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 DDO. This is O is off diagonal, DO, and well OO. And then they compute the functional, the tau really, and they find that in these 2 cases they turn out to be 0. But curiously enough, in the second and fourth case, they get non-trivial torsion. Here, this is.
You said the Dirac operator is 0, you mean the torsion.
Did I say Dirac operator?
You said it's not identically 0.
This is, yeah, the Dirac operator, the torsion is not identically 0. Yeah. And this is my lack of tech skills. This is the metric functional on the manifold, and when I say metric functional, it just means that you take the Sugar-Riemann metric and integrate over the manifold with respect to the volume form, and yeah. And this is nu f is just the L1, not the L1 now, it's just the integral of the functions over f. Note over here that this case, no off-diagonal elements, no diagonal elements appear, and it's as if the calculus, the value of this part of the function lives entirely on the D2 part, whereas this involves 2 diagonal type 1 forms. So this is a very rushed recall of the results of this paper. So then we go over to.
So perhaps it should be also mentioned that for the spin Dirac operator of spin manifold coupled to torsion.
Coupled to torsion, then torsion recovers.
Torsion as integrated, contracted with these three forms.
Okay, could you repeat what he said because he was too far from the microphone?
Yeah, so what he said is that if you have spin Dirac manifold, and if you couple the Dirac operator with a torsion operator, then this first expression will again recover the torsion. It will recover the torsion of the it will recover the torsion of the operator which you coupled it with. Yeah. Yeah. Right. So then we go on to second order differential calculi on spectral triples. But this is going to be a new modification of the old way of constructing of algebraically approaching the Kohn calculus on spectral triples. So this is a recent, I think it's still a preprint by Meslan and Rennie. And so to discuss algebraic torsion, we require a few more ingredients. So first of all, what we need is that we need to know the definition of what junk 2 tensors and junk 2 forms are. I should have switched anyway. So it is this construction. The top one is by Kohn. It is essentially when you pass from the tensor of 2 one forms to the 2 forms, or you do the derivation of a one form, then just applying, like, just if you are derivating sum over ai dbi, and if you just take the commutator of ai with d, it need not be a well-defined map, even need not be a well-defined set. So the trick is to throw out the, as you can see, the name is junk forms. The trick is to throw out all these bad features. What Mesla and Rennie did, the modification was that so instead of going to classes of operators, they stay in the level of tensors of operators. And as you can notice is that if you multiply these, so if you multiply this set JT2D, you arrive really at J2D. It's just that the tensor is removed by the multiplication of multiplication between bounded operators.
But the tensor is over this balance in terms of product.
The tensor is over the algebra, yes.
The balance is not algebra.
You can, so the star algebra, I can take these to be finite sums. It will just be.
It's algebraic, but not over C.
Not over C for sure. No, it's over A. It's over the algebra.
Okay.
But it's not on. So it's because it should be on the screen. Otherwise, it's usually.
It should be on the screen. Yes. It should have been in the slides for sure.
Yeah.
Yeah, because otherwise the multiplication between bounded operators is probably not well defined. Yeah, I have to think a little bit, but it's probably not. Right. Yeah. So this is first new.
I'm sorry, but it's because I don't agree. I mean, it's irrelevant as long as your tensor algebraic multiplication is well defined. It's just not star homomorphism or anything. But it is well defined on any algebraic tensor product, balanced or not. I mean, balanced tensor product is just intermediate quotient before you really multiply.
I'm just worried about if these DEIs could become something nasty.
No, that's okay, because you can multiply the operator from the right and from the left.
Yeah.
From this, from C or from the function.
Well, okay,
Exactly.
Okay, it descends. Okay.
It's well defined.
Yes.
Right. So,
I agree.
so note that under multiplication, JT2D.
SUGATO, can I have a question?
Of course.
Yeah. Can you identify this JT square as just a kernel of the map from one forms tensor one forms over the algebra into the two forms?
Yeah, good question.
I mean, a part of that, or at least a part of that. I mean, it's generating that.
It's part of that. Yes, JT2D is at least part of the kernel of going from one forms tensor, one forms to two
Well,
forms.
yes, it's bigger. In the John tensor in the second line is smaller. Later, I think we will construct. We need a gap.
But I generate it.
It's I am not sure it is the full thing. So there can be stuff which is not in JT2D, and it's a tensor, and its multiplication still lands in J2D. Does that answer your question?
I think we'll see in the next project.
Yeah, so I will.
Yep.
It's a two tensor which is not in JT2D but it is in J2D at least in one case. So yeah.
Okay.
Right. Right. So yes. So then comes the notion of Hermitian second order differential calculi. So it is the tuple of the space of one forms left a valued inner product on omega 1d, and psi is a bilinear idempotent on the space of two tensors. That is, first of all, psi square equals psi, and moreover, image of psi has to satisfy this containment that, okay, this is another typo. This should have been M inverse, multiplication inverse of J2D, because we from the previous slide we saw that JT2D is contained in M inverse of J2D. So image of psi has to satisfy this particular inclusion, and psi is compatible with, so remember that T2D comes as, since it's a tensor of bounded operators, it has its own involution structure, which is that X tensor Y whole star goes to Y star tensor X star. So psi has to be compatible with the involution of the bounded operators. The image of identity minus psi is denoted by wedge 2D and is called the bimodule of two forms.
Complementary.
Sorry?
Of the complementary project.
Yeah. So the idea over here is essentially to treat psi like a symmetrization map, and like that's the generalization, that psi is like a symmetrization map, and the identity minus symmetrization, that is the anti-symmetrization, is isomorphic to classically it is isomorphic to the space of two forms. And I note that I have not used the symbol omega 2d and used wedge 2d, because in the case of cons bimodule of two forms, the image of psi is equal to M inverse JT2D. So in that case, as Andre was asking whether it's the whole kernel or not, in the case of classically these are equal, but I will soon give an example. And classically this omega 2d is identified as the multiplication of the two operators, two omega 1 d's, and then the quotient out by the junk two forms. But this need not generally be the case. Right. So another ingredient for second order differential calculus, because we just have space of two forms at the moment, is to define the exterior derivative, which is, again, this depends on psi, because d psi is a map going from omega 1d to wedge 2d. This, I would say, generalized two forms, which satisfies d psi compose d equals 0, which is the usual analog for the usual d square equals 0. And its d psi has these left and right Leibniz rules. So look at the middle term. The middle term lands perfectly well in the image of identity minus psi, or the kernel of psi. But there is no a priori guarantee that dA tensor omega would land in the image of IDA tensor psi. So we hit with an IDA tensor psi over here and one over here. Now, the real crucial part here was, this is part of the Mason's work, is the crucial part is that the image of psi need not be equal to the pre-image of the multiplication map of the junk 2 tensors, as long as we remain in the level of 2 tensors and not go down to classes of operators. So the question was always that what happens if sum over AI dBi is 0, and then if we apply deep psi and it, like if you do a commutator, it need not land in the it need not be well defined. Well, because if we just put b equals identity, then saying that 1 minus psi, putting the projection of 1 minus psi, so if this were equal to be 0, this would be killed by 1 minus psi. Right, so this inclusion really is an important part of the construction. So again, let's do this exercise for the 2-point space. So recall that the space of one forms on the 2-point space is generated by a single element. The left A linear valued inner product, which I am chasing, is just determined by this particular equation. It could at most differ by a scalar. So we have the inner product. Now we talk about the psi map.
Sorry, may I ask another very stupid question? When you have an inner product which is valued not in numbers but in algebra.
So I'm essentially saying Hilbert's system on this. Yeah.
But I'm wondering, does Cauchy-Schwarz inequality work then?
Hilbert modules?
Yeah. Because I'm teaching here, so this is why I asked this question.
Cauchy-Schwarz.
Well, I mean, there is number inequality, but here it would be in the sense of positive elements.
Yeah, but then that's a different question.
Okay. But it's in a sister algebra, so we have lots of tools. I'm just wondering if there is a chance.
SISSA, Cauchy-Schwarz, Bujakowski.
SISSA, Cauchy-Schwarz, Bujakowski. Voila.
That's Russian.
Okay. Sorry for it.
No. Yeah, this is interesting. And yeah. Right. So in the case of psi, in the case of the 2-point space, psi is unique. It can only be taking this 2 tensor to 0. Otherwise, the second order differential calculus becomes trivial. This modified second order forms is generated by this one element, and deep psi is very trivially defined as this thing remains, and deep psi acts on E plus and spits this thing out. Note that in this case the Conlandi calculus agrees with the modified version, because
this is in a book by
Yeah.
so you should call it Con.
Okay.
I mean, I could not.
Okay. The concept
It's much later.
is this modified version perfectly agrees, and in fact there is a unique non-trivial calculus on the two-point space. It is just the universal calculus. So as long as it's a non-trivial calculus, it has to be the same thing.
Just a remark. In this very simple example, this you have the jump forms and the pre-image of jump forms on the jump tensors. There is no room for psi. So if you go back to the previous slide, so the definition should be, you see this JT T square is contained in the image of psi, is contained in the image of JT2D. In this case, the two ends, they are both zero, so there is no room for any psi.
Sure, that's an interesting remark.
That's the case for the two-point space.
Right. Thanks for that.
I know it was here from my microphone. You can repeat.
Francesco, did you hear what Jan was saying?
I think everybody left.
No. People are here. Francesco?
You can repeat this.
Yeah, okay, I'll just repeat it.
Yeah, okay.
So what Young says is that for the two-point space, both JT2D and J2D are trivially zero. So there really is no, I mean, one way you can see that there is no choice for psi is that the image of psi is just nested between two zeros, two empty sets rather. So yeah, that could be another way of looking at the uniqueness of psi. Where am I? Right. Two-point space continued. Right. So now, for the example of double manifolds, and this gets a little tricky. So remember that we had decomposed our the genetic space of one forms into diagonals and off diagonals. We now further decompose it into 4 parts. So basically, the 4 blocks of this 2 by 2 matrix of operators. And well, how general it is to assume them to be orthogonal, we can be, a source of debate, but nevertheless, they are orthogonal in some sense. Then comes a nasty set of equations where essentially after declaring that each of these pieces are orthogonal, I just need to define the inner product on each of the blocks. And now recall this is a Hermitian product, but on the doubled manifold, but on the classical manifold there does exist its own natural Hermitian product. So I define the top diagonal block to be an element taking values. So this value is this takes values in C infinity n, and since these are sesquilinear, like conjugate linear in the second one and left linear in the first one, if you do the UV star computation for these generators, you find these pieces. And similarly for the bottom diagonal, we have the analog as the top diagonal. So this is okay. This is at least one concrete inner product defined on my second order differential calculus. It is still it's a long check to see that it satisfies all the various properties, but
First order.
no. So okay, fair enough. First order differential calculus. Yeah, I haven't come at the moment. Yeah. All right. So again, like I had to do it piecewise to define the inner product. Psi I will also define as terms of tensors of various combinations of diagonal and off diagonal. So there are 4 types. Is it did I lay over? No, I didn't. Okay, there are 2. So the first type I choose as to define is diagonal tensor diagonal, and if you just take a quick glance, you can see that this is this behaves very much like the symmetrization map, that it is just half times the basic flip. That it is again well defined is a check, but well, it is. Next, I define on the diagonal tensor of diagonals. Here, mind you, it's not exactly a flip, because this term over here, the omega 1 plus omega 1 minus diagonal, over here this gets another twist in the second leg. So we could call this a twisted flip maybe. I'm sorry, twisted symmetrization maybe. And then, as you can guess, for off-diagonal tensor diagonals, we again do the same thing, that this piece over here comes to the first leg, but with a twist. But then the last case is tricky. So psi can, for these copies, can be defined to be either 0 or identity. And both are well defined and both satisfy the inclusion condition that JT2D contain. So that's a check, but at least you can see that if you multiply over here, okay, well, I'll get to it. Both of them essentially satisfy. I'll show part of the result over here. So for the choice of psi prime, at least for manifolds M of dimension 4, this construction coincides with the standard Korn calculus on doubled manifolds. When I say coincide, I mean equivalent, in the sense that wedge 2D is isomorphic to omega 2D as bimodules.
I think I understand what you mean, but I think that's not exactly true, because the psi lives in this T2D, which is something like omega 1.
Isomorphic. And it's equal.
Well, yes, probably possible representation, yes, but eventually.
So, what I had mentioned over here is.
It's. I think for the psi prime, so we have the image is equal to the. So sorry. Could you go back to the?
Go back.
Here. I think that case is that you have for the psi prime, you have the image of psi is on the right hand side is equal to the pre-image of J to D tensor. So that's the case.
Yeah. Again, it should have been M inverse J to D.
Yeah. For psi prime, that's the case.
Yeah.
Which is somehow we should be able to recover Korn's calculus.
Yeah.
That's the.
Yeah, so, okay. All right, so what, as I was saying, that if we take psi prime and leave the other psi's as it is, for the other blocks, then the space of two forms according to Messer and Renyi, and the space of two forms according to Kohn, they are isomorphic as bimodules. However, one lives as a class of as a set of classes of bounded operators, and one stays as tensors of bounded operators.
Just one more remark. I mean, it's just the way we consider these two psi's is the following. So if you consider psi prime, which somehow agrees with Korn's, so then it will kill because 1 minus psi prime will kill the torsion requirement.
Wait.
So that's why we. That's why we focus on the.
Spoiler alert.
Yeah. So spoiler alert. Yeah.
Okay. Yes.
Yeah. It's just the next line, and I didn't even do the proof much as it is. Okay. No. But first of all, check the well-definedness of psi. So I mean, the fact that JT2D is contained in psi is something that has to be checked, and we check only the case for where this thing is mapped to 0, because as you can see that the image of psi prime is bigger than the image of psi is strictly contained inside image of psi prime. So if just checking this satisfies showing that even psi prime is well defined.
Yes.
Right. Yeah, and holosymmetry, blah blah blah. Sketch of the proof. So it's a few steps. So first of all, I had defined, given a notion of inner product on one tensors. So I extend this on two tensors by, so keeping in mind that this has to be linear in U and V and antilinear in W and X. This is I think the standard construction for Hilbert C-star modules. If not, we'll see later. So this thing is again, this whole thing is linear, and then it is linear in V and antilinear in X, and of course it is antilinear in W, and all things line up. So to show that, so step 2, what I do is I show that kernel of psi is orthogonal to image of psi, because I know that psi is an idempotent, so T2D does really break as sum of kernel of psi and image of psi, but to know that they are orthogonal in the sense of my inner product. So for this, I observe that kernel of psi is generated by this straightforward antisymmetrizer, this twisted antisymmetrizer. Notice that it is F plus, F minus, and here is F minus, F plus. And we decided to, by fiat, define that psi of this element is 0. So these three types generate kernel of psi. And image of psi is defined by just these two elements, that is the on-the-nose symmetrizer and the twisted symmetrizer. And then it's just a stupid check of computing the 6 inner products and just to find them that these are all equal to 0. Right. So this thing is that, so we know that JT2D is orthogonal to kernel of psi, and T2D really does break into kernel of psi and image of psi. So, wait, just a moment, did I miss something? Oh, no, okay, so this is another, I have to check another thing, which is that a generic element of JT2D, which has a very different description than elements of image of psi, we have to check that a generic element of JT2D is orthogonal to kernel of psi, again done with the 3 generators. So since psi is an idempotent, we have the orthogonal decomposition. JT2D is perpendicular to kernel of psi, so it is contained in image of psi. Hence we conclude that we have a well-defined second order differential calculus. This thing could probably be checked in other ways. I think Messlin and when they do it for, I think, the toric manifolds, they do something else. Right, so finally I come to the notion of algebraic torsion, which is, well, I mean, and try to at least compare with Dobrowski-Shikaz and Zalesky, that does it match? Well, to define algebraic torsion, so algebraic torsion is unlike spectral torsion, which they had defined as something inherent to the Dirac operator and not tied to anything else. Here, it just depends on the regularity of the Dirac operator. Algebraically, one of the ways torsion is defined is torsion of a connection on a second order differential calculus is defined. So here's the definition, which is that modified suitably for our setup, is that a left connection is a map from omega 1d to T2d, satisfying, so it has two parts, it has a left linear part and a left Leibniz part. And torsion of a connection, which is now a map from, so it is a map dependent on psi, by the way, and T nabla psi goes from omega 1d to wedge 2d. Maybe a psi should be added over here as well.
Sorry, but I'm now confused about your level of generality. So what are your standing assumptions? I mean, are you still talking spectral triples or?
Yeah, it's still, I mean, this could go to any second order differential calculus as long as this thing holds and this is isomorphic to which this is isomorphic which one? Kernel psi is isomorphic to the space of two forms.
Yeah.
Or one way or the other. I skip for that.
Yes, yeah.
Maybe we just stick with the spectral triple because we use D, the capital D. So there is always a D. Right?
In our case, it is.
In our case, yeah, for this topic, we will not be talking about. But yeah, one of their papers, they do it for.
You cannot compare something which.
No, yeah, so the comparison result won't work. Yeah, comparison result for your paper won't work if you don't do it on this generic, for sure.
Yeah, but if just for torsion, it can be defined more generally by less.
Torsion itself, algebraic, can be defined more generally.
No. I mean, so you mean this is the generality or something even more?
Even more.
Yeah, even more. It's just a connection and the exterior derivative. That's all. You can talk about torsion.
And the second order calculus, yeah.
Yeah, a connection.
Oh yeah, sure, yeah.
You need the notion of connection and the notion of the
and the notion of the
exterior derivative, which means the differential calculus.
The multiplication between two one forms to give a two form.
Yeah,
the wedge map.
That's the exterior derivative.
No, that's not the derivative.
The differential calculus is like we have one form, two forms, you have the map. It's exterior.
Between them. Okay.
But also you need the multiplication map from
tensor product.
Tensor product to go to omega 2.
Yes, that's true.
Yeah. So this 1 minus psi essentially does the job of wedge over here. Okay, again recall that the space of one forms is generated by a single element as a left module, and the space of two forms is generated by this single element. Then the classification for arbitrary left connections on the 2-point space is given by nabla 2 on this one form is parameterized by two arbitrary complex numbers and then multiplied with the generating 2 form. Note one thing, I will go back a moment please. Note one thing is that it is sufficient to define it on generators, because after defining it on nabla omega, we know how the Leibniz part works. So it's just about defining it on the generating part. That's the linearity is all that matters. So C plus minus completely and then torsion of this thing is completely then determined by this particular equation, for the simple reason that I said that it has left linearity and then left Leibniz.
Perhaps it should be added that this maybe I should not.
Should be added that. No, sorry.
It's such a simple solution. You just sit here and everybody can hear.
Okay, so that is definition which he presented as a map from one forms to two forms. Actually, is dual to what geometers used as for a torsion before, as a tensor.
So tensor from vector fields, two vector fields to one vector field. Yes. Yeah. But it is linear on the C-linear on the first leg and C-linear on whatever. So C-linear on one leg and F-linear.
It's more than C-linear. It's You can factor out functions.
On one leg, and on another leg you can only factor out scalars.
No, it's a tensor. It's a tensor.
It's a tensor.
So you
You
can
can
have
factor out
multiplication by functions in geometry.
Okay. Okay, are you talking about torsion or? Okay, yeah, no, torsion for sure, torsion for sure. Torsion, yeah, torsion is a left A-linear map for sure, yeah. Torsion. Right, so torsion completely determined by this thing. Let's go. And note here, so I have not spoken about metric compatibility. I will not be speaking about metric compatibility in this talk, so there's not much sense in talking about Levi-Civita over here, but we can see that the only torsion zero connection over here is the Grassmannian connection. So it's only a question about looking if the Grassmannian is Levi-Civita for some matrix, or otherwise it does not admit
So means C plus, C minus equals.
0, yeah. And then, so, yeah, so the nabla 2 on this single generator is going to be 0. So that's the Grassmann. Yeah, I kept on switching between C plus minus and Ci, yeah. Now, this is the
Total recall.
recall, total, yeah. So, again, recall, I keep saying because there are so many moving parts over here. So, recall that the space of one forms breaks into diagonals and off diagonals, and then Dombrowski, I'll say. So, I have found out that they satisfy these things. So, we want to mimic, we want to see if we can arrive at some or all of these equations, these formulas through the algebraic route. Now, firstly, I just compared for the 2-point space, but let me just go back. Here, so the 2-point space is as if you're just taking 3 off diagonals, so you're just forgetting all the diagonal ones, and you're just taking 3 off diagonal forms. So it is on the 2-point space, the only thing to check is whether the 4th equation holds, where one has to remember that f1, so f plus minus i's are now functions on a point, so they are complex numbers. So we stop short of saying that we are dealing with a zero-summable spectral triple, even though it's a point cross Z2. But we replace m with 0, and instead of the non-commutative residue, we replace it with the integral over the counting measure, that is just the matrix trace. On the algebraic side, so we had found these 2 tensors, and now we want to arrive at scalar. So we take the Hermitian product and then the trace. On the algebraic side, we find that we get this particular formula, which would be the same if we had replaced this W with the integral over the counting measure, and this with just the integral. And we have a match if C plus equals 1 equals minus C minus. So we are happy, partially. Let's see if it works on the general case. So since we are looking for, so what the spectral torsion functional was something intrinsic to the Dirac operator, to the spectral triple, and there was no choice of connections. Well, what would be the natural thing to assume is intrinsic to, which connection would we consider to be intrinsic to a manifold, Riemannian manifold at least, is the Levi-Civita connection, let's say, even though a priori just a torsionless connection works. And then we consider this product connection over the double manifold. So we call that we had a choice of psi, whether this maps to this piece is identity or is it, if it's zero. So when we evaluate the map T nabla psi prime, then at least for dimension m equals 4, we find that it is a zero map. So if we did the conformalism even on the dimension m of equals 4, we lose out even on the result that we had, assuming m being a point. And so instead we choose psi to be by phi to be equal to 0. The torsion map T nabla psi decomposes into in the following manner to torsion, like how it's this describes how it's constituted by torsion of the individual connections, and then what we say is that we evaluate this integral where we apply the torsion on an arbitrary one form and take its inner product to omega 1 tensor omega 2. I forgot to mention one thing. Let me again go back a moment, please. So, in this, okay, never mind. So this was written a long time back, which is that this torsion functional was taken to be a trilinear functional, whereas here I have Hermitian on the second leg. So in order to turn it back into trilinear really, we apply the involution of the bounded operators over here again. And then we evaluate the integral. Now this is, I would say, partial or results or whatever. So of the four formulas that we had, for the diagonal, we see that this does absolutely work and it gives us equal to 0. Similarly, for this type of DOO, this again gives us 0. This again matches DSZ. The fourth one again matches DSZ, but we had this is just like in the finite case, except now that instead of having f plus minus i's to be constants, these are now functions on C infinity m. So again, as in this previous case, for C plus equals 1 equals minus C minus, we have agreement with the paper over here. There might be a problem with the remaining second equation, and maybe a little more work needs to be done to address the last remaining formula. And I think I'm going to wrap up now. So the main result is...
Well, you still have half an hour.
Okay, so maybe more questions then. So for our constructed second order differential calculus for the double manifold, and for our, so there's a choice of the second order differential second order differential calculus, and our choice of the connection nabla 2, that is C plus equals 1 equals minus C minus. The functional, this functional dual agrees with 3 of the 4 spectral torsion functional formulas of this paper, and so the conclusions are limited, but I think fairly interesting in the sense that we detect torsion using algebraic methods, which a priori algebraically, I think mostly people chase Levi-Civita, and usually there is this thing of for every matrix there is a torsionless connection which is compatible. So here we have at least an example where there is clearly a dearth of supply of torsionless connections, and as far as we know, this is the first concrete example where the differential calculus construction of Mechelin and Renyi departs from the one due to Kohn. And that is all I have to say.
Okay, so thank you very much, but you still have half an hour and so expand, improvise, expand whatever.
So, right. I can.
You were warned that it's 90 minutes. So.
So it might possibly be that, where are my metrics? Right, so this was supposed to be something I was going to be talking to you regarding the problem I mentioned. And so, yeah, the thing is that this thing of going to like building up a valued inner products on two tensors from one tensors, this it might be that first of all, construction of instead of constructing a valued, what Young always insisted is that go to C value, that is chase an integral. And so for the one forms, maybe we don't need to do the block business. We can maybe take the genuine. So if you're doing the inner product of u comma v, it might be that you take integral trace u v star, which would take care. It would land in C, but it would take care of the off-diagonal things, where I keep emphasizing that the diagonal value things should come. But here again, and then we just pretend that it is. So this is now for anything. So here, if you see that, if we remove this bracket and if we say that we are u tensor v is now my new u and my new v is w tensor x, then we might have to do integral trace of u v x star w star, and I just checked, and the remaining one works.
So
maybe I can give a general comment. I don't know why at all we were okay. That previously, before this torsion functional, okay, which is depending on three one forms, which are these one forms are defined for any spectral triple in principle, with bounded commutators between Dirac operator and the elements of the algebra, but also for twisted spectral triples in principle, it's bounded commutators are non-bounded, but we have to modify it due to Coulomb-Scalici probability. So you have first order differential calculus for the spectral triples of kind of automatically. Particular one, of course, coming from some universal calculus by quotienting something, of course. Of course. But we don't have second order differential calculus, and we don't have connections at all. These Dirac operators are completely abstract guys. Are operators. Okay? First of all, they are operators, not only operators, they operate on the Hilbert space. As in quantum mechanics, this is what Alan Kohn always says, underlines, okay? He goes to Helgoland, there was Heisenberg there, and he invented matrix algebras of operators and operators. So quantum mechanics is underlying, let's say, example for Alan Kohn. Always operators. I mean, whenever you want to go really too deeply to the ground, operators in Hilbert space.
Unbounded?
Dirac operators are bounded, but essentially here we also ask for inverse, but it's not really inverse. We can just modify it by small perturbation. This Dirac operator is very modulo compact, for instance. It's in the sense of parametrics and so on. So these inverses and d to minus n work well, even if this is not invertive, strictly invertive operator. Okay, but it has compact resolvent because of that. It doesn't differ much from its inverse times the operator is not much different. Differs compacts only from one, okay? So that's the quantum geometry.
our non-commutative geometry in the sense of cons. While previous, okay, and before this torsion operator, a torsion functional, we defined, there were some other functionals defined. One was non-commutative integral, which was this calligraphic new integral of, which is integral, usual integral of manifold, the usual case. And also there was another integral, which was called scalar curvature integral, which was just discovered by Kohn in the 90s, I think. And we introduced a few other functionals, non-commutative functionals, okay, which agree. There were metric functional itself, it appeared in the formula for the torsion in the last slide, okay. And also another one, which is Einstein tensor functional. It, in the classical situation, actually covers this integral of the Einstein tensor itself, which is very important for equations, of course, for the general relativity equations. So we can also define, though it is not in the paper, we can also define a Ricci tensor. Ricci functional, something which covers Ricci tensor. Not yet full Riemann tensor, we don't know, probably it's not possible with this method, who knows. So this is true.
So Ricci is important because that's what you have in the Einstein equation, right?
No, you have Einstein tensor, strictly speaking, but classically it's Ricci minus half.
Exactly.
Scalar curvature times metric tensor. So all these three ingredients we have, and we can see they match the equation that Einstein tensor is equal to the Ricci minus scalar times the metric tensor.
Yeah.
So far until, okay, torsion, instead, as I said, was in geometry, was just a linear antisymmetric map from pair of tensor fields, vector fields to vector fields. You could generalize this a little bit to non-commutative geometry as soon as you have derivations of algebra. Of course, vector fields are derivations of the algebra functions on the manifold. Okay, so you could go further. But this approach of Kohn, spectral tree, is much more general. As soon as you have derivations, enough number of derivations, you can define in principle spectral tree. Okay. But not vice versa. You can have spectral trees on something which doesn't have any derivations at all. So no vector fields. So differential forms are better from this point of view. And they were used in this reformulation. I think it was, I forgot the first one, maybe someone knows. Dualized this torsion as a map, antisymmetric map from vector fields to vector fields, as a map from one forms to two forms. Okay? I think Frolik is one of the first papers, Frolik with two other collaborators. Okay? Grandjean and Rectangle. So they did this in parallel with this developments of Kohn many years ago, and it was taken by various groups, including Kolkata groups, including Majid Beks, including a group in Scandinavia, a group in Canada. There were various people trying to define connections which are torsion zero, okay, and also metric p-serving, so Levi-Civita connection.
Yes.
But not recovering torsion itself. Okay, so torsion itself was mainly not studied in the usual approach to the algebraic approach to calculate. So trying to marry these two things, okay, marry the spectral operatorial Lacan and this algebraic approach, we had to take playing ground which you can do both things. So first of all, you take differential calculus related to spectral treatment, and then try to compare these two definitions much somehow. And this study case, which is this particular example, that the simplest non-trivial algebra Z2 of 2 points, okay, C2, or this double manifold was the playing ground to check if they can be matched or not. And with some adjustments, it seems that it's the case. Okay, so that's what I wanted.
Thank you so much.
This was very important. I mean, this is how the talk should started. Because I find it as a very important comment. Now I understand what you are talking about. Okay, and the second call for Yeah,
Yeah, just one more.
but please, here.
Okay, it's just one more remark. You see, when you talk about level chiplet connections, there are 2 points. One point is torsionless, but here we care about torsion, not torsionless. The other point is compatibility with metric. Right? So that's quite difficult questions when I look at the Mason Rennie's approach. Like most of the efforts was devoted to that part. So okay, so we can ask the similar question here. So how to describe this metric compatibility,
yes.
right? So now in terms of a Riemannian metric, so it's like now in this NCG dictionary, it's just about spectral triple. So that's why we are looking for this agreement with this spectral triple and this algebraic torsion function. I mean, in a sense, if they agree, then it's sort of a replacement of this metric compatibility. Because in the quantum setting, like lots of this algebraic language you learn in Riemannian geometry, right, cannot be just transferred directly, right, to the spectral setting. So now it's like one side you have this spectral function, and really the function, this trilinear function is quite intrinsic. You just need a spectral triple, no more data, right? So it's just a unique one. And the other ones for the algebraic side, you have many options. You have this Kasai, which gives you any Kasai gives you a calculus, and then you can have a free choice of connections, right? So when you choose find the right one, if they match, sort of there is a compatibility we are looking for. That's why we are doing fight with this computations.
Yeah, there is much more to work because we have other functions. We have metric function which we can now compare with metric definition in this algebraic. Defining algebraic.
Well, what I'm missing is some examples, like.
Well, these are first 2 examples.
Yeah, but wait a second. I mean, I'm talking about you haven't given me a single example of a double manifold. Yeah, but something where you compute something. You show me.
So-called Commutative.
Yeah, this is Commutative. This is what I showed you. Yes.
Which was precursor of this German Noncommutative version of the standard model.
Yes.
Okay, so it's not model, it's on the line.
Okay.
Yeah, so I mean, this is very example which we have non-trivial torsion, because the other examples in the spectrum are Andrzej torsion, Zalewski, which I can list them also. For instance, quantum group SU2. With this Dirac operator, which we defined, that comes with torsion 0, actually, according with spectral torsion 0. So the other were not so interesting for us. We wanted to compare something which has no zero torsion.
Yes.
Yeah, we're exploring examples by examples. That's right? So that's because we are finding like this algebraic and spectral version disagreements. That's we start with just one very concrete example there.
And Andre, how about you? I mean, you are somehow here also. Can you show yourself, perhaps? Oh, that's really good. Okay, not artificial intelligence.
No artificial intelligence. I'm just, not, with in my best form as I caught COVID. So that's.
Oh, so sorry.
Yeah, unfortunately. I mean, I have no questions. I mean, one comment that I can make. I mean, I mean, generally torsion, I mean, is purely I mean, the way it was defined, I mean, algebraically, it's purely algebraic. I mean, then you don't need this tricks with psi, whatever. This is just a map. When you compose the connection with wedge and subtract D. This, however, highly depends on the choice. What is the second order differential calculus? So it's omega-2, and this is one of the usual problems. I mean, in the constructions and sort of ambiguities. And the spectral approach, I mean, takes some sort of different attitude. I mean, it forgets about connection. This is one of the interesting points also that, in this general setup, when you start taking the differential calculi with D, so this thing, you don't know a priori that D has a torsion or not. So there's a good question. what happens if D has a torsion? I mean, in general, I mean, not classical case. Classical case, we know it doesn't matter. But in the non-classical case, we don't know. So if D has a torsion in the beginning, would the, so to say, the entire construction differ from D without torsion? So that's a, comparing this spectral and algebraic things is slightly different. I mean, in a spectral approach, there's no way to see the connection. The connection is hidden already in the Dirac operator, and everything is given by the Dirac operator. So this is, circumventing the problem. What we know more or less, this is from the ongoing work with Ludwig and to further collaborators, my former PhD students, that what we know roughly is that this torsion functional would detect only antisymmetric torsion. Am I right, Ludwig?
Yes.
Yeah. So, and torsion could be also slightly more general, not only antisymmetric. So there's a lot of questions. There are a lot of problems. There are a lot of questions, and it's time. This is something we want to explore further, and more people to join the research if there are any willing.
Okay, that sounds like an invitation
To Krakow.
Yeah, to Krakow, yes. Thank you so much, Andrzej. So I think that by now all the co-authors and collaborators commented, and most of which Hickson are not on Zoom, so we cannot ask. Can you go back to your last slide, to this theorem, right? Before conclusion, so penultimate slide, yes. So could you somehow hint at the proof? How do you prove it?
The proof is again, it is evaluating the.
So this is a sketch of the proof.
Yes, sketch. So I mean, so we construct the Hermitian E-valued Hermitian product, take the trace. So the trace lands in C infinity m, and then this integral is the standard integral of the over the manifold given by the volume. So
your manifold is compact from the beginning.
Yes.
Okay.
Yes.
You never said
close.
Close. Okay. Okay, close. Yes. Sorry. Yes.
Maybe I just make a. I mean, the proof I think is conceptually is easier. It's like because it's almost commutative manifolds. It's constructed out of a tensor product structure. So, and then on the manifold, we choose the Levin-Shibler connection, which means the torsion free.
Yes.
Well, so this quantity, this non-zero part, is just derived from the 2-point space.
Yeah. So
discussed at the beginning. So it's like a sort of for that part agrees. So that's sort of basically not hard to pass to the manifold case, because on the manifold we choose the torsion free connection. So it's like basically if you have an agreement on the 2-point space, and then we just upgrade it a little bit, it's almost non-commutative.
But why just take the product? Why not take a covering?
Yeah, that's the.
So.
Yeah.
Yeah. This is a non-trivial covering. It's a non.
By your own comment. What you are basically saying is that blowing up a point in a manifold doesn't change much in this consideration.
Here, the non-commutativity comes from, so of course the function algebra is commutative. The quantum part comes from the fact that even on the 2-point space, the one forms is not a symmetric binomial.
Yeah.
So that's where, that's where you basically the geometric intuition probably lose. We cannot say, okay, this is a sort of a trivial bundle or something. So because the module is not symmetric, that's what this quantum phenomenon.
So we can compute distance between any 2 points of this two-shifted stuff. And if this parameter phi is 0, it is infinite distance. If phi is non-zero, I mean, this is all stuff. I mean, common phi.
Yeah, I remember it from my youth. Yes.
For spectral for functionals for spectral frequency.
Yes.
For characters on commutative algebras.
Yes.
So distance can be computed. It can be also taken to depend on the, I mean, this distance is then, and this is just a product, so distance is metric product, not only the product of functions. Metric product in this metric sense, okay? But we can make it depending on the point of x. So it will be this surface can touch close count. So there are like brains in strict theory.
Okay. But still, so what's your answer to my question? Why not covering? Why just a trivial?
No. Next step.
Yeah, I mean, this is a trivial covering, so non-trivial covering.
Yeah, exactly. Okay.
What should be a good time to start?
Okay, so let me ask anybody on the Zoom. Tomek, Adam, go ahead. Tomek, unmute yourself.
Okay, so I had the same, maybe not complaint, but the same question as you posed just. It was about this. Why this coverings? And if coverings, why double coverings?
No.
Yeah. So what is the problem with other?
Simplest example.
I mean.
Okay, so I understand it's a toy example for more general story. Okay, but then you are talking about finite spaces. These vertical spaces are finite with a non-standard spectral geometry.
Yes, exactly. Yeah.
Okay, so I would like to understand better what is happening in this vertical direction. How much this geometry, the spectral geometry of this finite set, how is it different from the classical one? What is so special for this choice of this Dirac operator, this choice of this differential calculus? Because my impression is that since horizontally everything is classical.
Yes, and Levi-Civita.
Okay. And Levi-Civita even, okay? Then everything depends on this vertical direction.
Yes.
Okay, but still I don't understand. So I can understand some game with matrices, but at the end of the day, you are splitting everything and you are isolating what is dependent on what depends on this horizontal geometry and what depends on this vertical part. But at some moment you stopped analyzing this vertical direction, because if you expect some phenomena related to this vertical geometry, everything should be first computed for one point base. Okay, and then you can start posing some questions, some conjectures, comparing things, because to me it's not clear what is happening when the base is consists only of a single point.
Okay, yeah, probably I can answer. So first of all, so basically this is a tensor product construction. So okay, so you are right. So every non-trivial, the torsion comes from the vertical space. The vertical space we take the simplest, like 2-point space. I mean, even this phi we choose to be a scalar, it's a number. So this is the simplest example. Of course we can, but the 2-point space, the geometry is totally different from the spectral triple point of view. As a just for this 2-point space, the one form is not a symmetric bimodular. Right? So that's the. So yes. So
on 2-point space, you don't have any classical one form. Okay.
Well, they have a universal one. Different.
Yeah. So it's like now because like in a classical case, usually like we wanted to play with the. I mean, in our example, we can still choose some non-zero. So for example, from the spectral triple side, you can take some Dirac operator which has torsion, which is not a Levi-Civita connection, and then basically you have torsion on the manifold, you have a torsion on the vertical space, and this algebraic torsion is just basically the the sum of both, right? So it's like, so basically, so the torsion, the non-zero torsion comes from the vertical. I think that's that's the first message. Yes. So it's usually just
yeah, but sorry, but my problem is that I don't understand this message. So what is the meaning of this vertical torsion?
Well, the vertical. So the meaning, I mean, there's a
map from one forms to two forms.
From the algebraic sense is you see it's somehow you measure the difference from the exterior derivative and this connection, I think, right? So it's roughly speaking, this torsion, algebraic torsion, is somehow D minus the nabla, so the algebraic sense. But also from the spectral sense, right? So you can take they call finite spectral triple in which the Hilbert space is of finite dimensional, and then you can still find the spectral torsion. Well, of course, the volume functional is just the trace. It's just right. So you have this notion. So for finite spectral triple, you have a Dirac operator. You have this torsion functional. Makes sense. And then you can one side you can interpret this torsion as a say linear functional. Right? So the geometric meaning. So probably I cannot answer because there is no geometry, classical geometry counterpart.
Yeah, but do you have some interpretation of junk forms for this your calculus for this finite space, 2-point space?
There is no junk forms.
No junk forms.
Yeah, for finite.
They are zero.
Yes. So zero, no junk forms.
Okay. So I can explain my problem with this context here, because horizontal what we are doing horizontally here is intrinsic, okay, with respect to some well-defined geometry. I would like to understand this construction as something intrinsic to some kind of geometry, but I cannot pinpoint this kind of geometry which is behind this construction. So because if this is some arbitrary matrix satisfying some being anti-Hermitian or of some parity, this is very big ambiguity.
Yes. So the intrinsic part is the following. So first of all, you have this trilinear functional from the spectral triple, it was spectral torsion functional. That's intrinsic to a spectral triple. You don't need any other ingredients to define this trilinear functional. And from the algebraic side, you have you see side, a differential calculus. You have the choice connection. On this slide, you look at this nabla 2. So nabla 2 is is parameterized by two complex numbers. So we choose them to be 1, 1. So we take them 1, 1.
1 and minus 1. But
okay, yes. For this particular one, it is completely, it agrees with the trilinear functional on the spectral side. So that's sort of so once the spectral side is intrinsic. So the algebraic side, you have some choices. We show that there are some very special choices, and these two agree. So I think that kind of answer your questions.
It's kind of
probably there must be some full classification of Dirac operators on 2-point space. Am I right?
yes.
Yeah.
The complex,
all the complex
finite SISSA algebras.
Wasn't it Andrzej Sikasz who did it?
Also contributed Andrzej to this, but Tomasz Krażewski and also other.
Okay, so if you have the full family of admissible Dirac structures on such finite algebra, can you produce your results in terms of this family? Do they depend on parameters in this family?
Probably yes, but not yet.
No, well, okay, yes, of course. So given any Dirac, so any Dirac in this family, right? So you have this well-defined spectral triple.
Yes.
Sorry, torsion spectral function.
Yeah.
Mhm.
And then now you fix one particular choice of this Dirac problem.
Yes.
And then next question you ask, so what are the possible all connections? Right? So and then you can find a very particular connection whose algebraic torsion function agree with this spectral triple. So that's yes, that's kind of our story here.
Yeah. So you mean these two free parameters C plus and C minus?
Yeah,
which
yeah.
at the end of the day become plus or minus one.
Yes.
Yes. You know the space of the possible connections is an affine space, right? So it's but there is
Only one which is Levi-Civita.
Yeah. In this sense, so we don't have this sort of a notion of Levi-Civita, but we have a sort of a very special one, which is from the spectral torsion function, right? So we ask which one agrees with the spectral torsion function. So that's the.
Okay, so maybe now I understand what I don't understand. So I would like to understand precisely the some kind of geometry making sense for this condition that C plus and C minus are plus minus one, for instance. Can be deduced from some first principles, not a posteriori by comparing some two spectral one and an algebraic version of torsion. So maybe there is some. So this compatibility, this coincidence of these two realizations of this torsion indicates that there is something behind this.
Yeah. Okay. So to give you some quick answer. Let's go back to which slides? The slides with spectral torsion. The definition, which is spectral torsion.
Oh, okay. Spectral
torsion.
And this is C1.
Okay. So you can look at the formula, right? So this is UV doesn't matter. There are some free parameter. There are two inputs. So basically, and then this W and this D minus to the absolute value D to the power n should be looked at together. This is the analog of the volume function, which is the integration on the manifold. Okay. So now the remaining ingredient is the WD. Okay. So on the finite dimensional case, on the vertical part, right, where the Hilbert space is finite dimensional. So this W with the D, this volume functional is just the trace. Okay. So our computation, I mean, essentially is not difficult. It's like we find a very special connection. The torsion of W is W2. So that's in this sense. So that's
okay. So you have this functional trilinear functional,
yeah,
and you are saying that your connection satisfies some algebraic condition of compatibility with this T.
Yes.
Yeah, agree with torsion of this D. Okay.
The algebraic
torsion of something I don't know. Torsion of this Dirac operator. Of this D with torsion. Previously, you could not even speak about whether this D has a torsion or not. It's Levi-Civita coming. If D is Dirac spin operator with torsion Levi-Civita connection, then it has this spectral torsion G. Okay? But if it's short, it has torsion. So we can measure the torsion of a spectral triple or of a Dirac operator.
So am I right to understand that if you go completely classical, and we'll take a Dirac operator somehow coupled with a connection, not torsion.
Exactly.
But would recover
this torsion.
Beautiful.
Okay. Good. Okay. Now I can say I understand. Thank you very much.
Excellent.
I'm satisfied with your answer.
No, I don't have any questions. Thank you.
Very interesting talk.
Okay. Okay, so I think it's time for pizza. So let's wrap it up. Thank you very much. Let's thank the speaker. And I stop the recording.